this lesson we're going to look at a particular kind of one of the more famous discrete probability distributions called the binomial distribution. So our objectives here, that we can determine whether an experiment is binomial or not. That we can, once we have determined it's binomial, that we can actually compute probabilities of those experiments, and then can be able to compute the mean standard deviation, and that we can do histograms for them. Okay. So here's a little cartoon I got from an old classic Calvin and Hobbes. Oh, good, a true-false test. At last, some clarity. Every sentence is either pure, sweet truth, or a vile, contemptible lie. One or the other, nothing in between. He looks at it, and he goes to flip a coin. So, we've got a binomial distribution, satisfies these conditions. A fixed number of trials, so each observation would be considered a trial. Only two outcomes, yes, no, true, false, right, wrong, things like that. And each trial is independent. One, flipping a coin 10 times, for instance, is sort of a classic example, because a coin doesn't have memory. It doesn't know that it's been heads the last 6 times, it's due a tail, so each trial is independent. And the probability of success is the same for each trial. So each time I flip a coin, the probability of getting a head or a tail is 50%, right, or 1/2. Okay, so let's determine whether or not the following here are binomial. If it's not binomial, let's state why it is. So pause the video here, see if you can use those properties. Hopefully you have those printed out, and see if you can give me the first two, A and B. Alright, welcome back. So a die is tossed 5 times. See how often a 4 occurs. So again, we just kind of imagine this experiment. You're tossing a die, and you want to know, does a 4 occur or not? So is this binomial? And so go back to the fixed number of trials, tossing it 5 times, only 2 outcomes. It either is a 4 or isn't a 4. Independent trials, the die again doesn't have memory. Doesn't say I'm due a 4, I haven't been a 4 in a while. And the probability of success is the same for each trial. So what is the probability of getting a 4? Well, there's 1 4, and you have 6 possible outcomes, so it's 1/6 each time. So this one is binomial. How about B? The die is tossed until a 5 occurs, and you count how many tosses this takes. So again, let's go back and look at this. So again, a die is tossed until a 5 occurs. You count how many tosses this takes. So fixed number of trials? No. We're not tossing it 5 times. We're tossing it until we get something. So that's going to be different each time. So it violates the first one. We don't have a fixed number of trials. So not binomial. Okay, so I've tried to kind of pair these up. From each pair, you'll have one of them that's binomial and one of them that's not binomial, and see if you can distinguish the difference between those two. This is the best way I could sort of do that, as opposed to having just a bunch of random ones around. So pause the video here and really see if you can think through these. Alright, welcome back. I know you're pausing it. A class is polled to determine if they have ever used tobacco products. Okay, so again, we're going to go look back. Fixed number of trials. We have 20 people in the class, for instance. That's fixed number of trials there. Only 2 outcomes. You either have used it or you haven't used it. Independent trials. We're having to assume independence on this, right? I mean, if you've got a husband and wife in there, maybe there's some research that shows that if one of them folks, the likelihood of the other one smoking is also is higher. But we're assuming independence, and the probability of success remains the same for each trial. So the answer is yes, binomial. So abbreviating here. A class is polled to determine how many cigarettes they smoke per week. So again, fixed number of trials, sure, but only 2 outcomes? No. We could have 0, 1, 2, someone could say 20, 30, 40, 100, 300, 1,000. So this one's not binomial. Okay, but the next pair. a random sample of 100 students is taken, and they are asked to state their major. And then F is a random sample of 100 students is taken, and they are asked if they are a math major or not. Hopefully you're getting a little better at this. So one of these has 2 outcomes, and one of them has more than 2 outcomes. Part E, right, has more than 2 outcomes. If I just ask you to state your major, someone may say nursing, someone may say biology, someone may say chemistry, someone may say business. So this one is not binomial. We have more than 1 outcome, right? More than 1 outcome. A random sample of 100 students is taken, and they are asked if they are a math major or not. So again, we have 100 students, fixed number of trials, math major or not, so that's 2 options. And we're assuming independence, so binomial. Oftentimes we have to assume independence on these when we may or may not be able to do that, but we do. What if I had another one? What if I said at random, we ask people as they're coming out of the library if they are a math major or not, and we count the number of students it takes before we get to 1. See, that would not be 1, right? Because we don't have a fixed number of trials. If we did that 4 or 5 different times, it could be different numbers each time. Okay, now let's compute probabilities of these binomial experiments. Here is the scary formula, right? This is a combination. You may have had this in an earlier class, college algebra or high school class. All this means, so n, they use an x in this book, cx is n factorial over x factorial n minus x quantity factorial. That factorial, remember, if it's like 5 factorial, is 5 times 4 times 3 times 2 times 1. So n factorial, whatever the n is, this is the number that I'm selecting. Number of trials in this case. X is the number of successes. P, probability of success, and Q is probability of failure. The good news is we're not going to be using this formula, but I had to show it to you. The calculator has this formula sort of pre-programmed in, as do all statistical software packages, including StatCrunch that we use in here in Minitab. So we're going to use TI or software to evaluate. We are not going to use the formula. So, example 2. Find the probability of getting exactly 7 questions correct on a 10-question multiple choice test. So first, we should really have a pre-question here, right? That is this indeed binomial? Fixed number of trials. We got 10 questions. Each answer we're assuming independence again. I mean, maybe if you get 5 truths in a row, you may decide to put false just because of the long string of truths, but we're assuming independence on that. And we either get it correct, incorrect, or correct, right? So it's either right or wrong. So find the probability of getting exactly 7 questions correct. So we're going to use a command called the Binomial PDF in this case. Binomial PDF. So I'm going to try to do this one live with you as well as the screenshots. Hopefully there's enough screen real estate for that. Okay, so we're going to have instructions here. I'm going to go to second vars to access the distribution menu. This is a distribution. And we're going to scroll down to Binomial PDF. So again, second distribution, and scroll down to Binom PDF. Right there. Press enter. So our syntax here is n, p, x. Just remember this is an alphabetical order. An alpha order. That's how I remember it. Okay, so what are we going to put in here? Go back to the problem and see if you can identify the n, the p, and the x. Again, the n, number of trials, the p, the probability of success, and the x is the number that we're selecting. So again, let me scroll back here. Let's look at the problem. It says, find the probability of getting exactly 7 questions on a 10-question multiple choice test with 4 choices. So again, let's go ahead and label it. It's probably a good idea to go ahead and label n, p, and x. So what is n? Number of trials here, we have 10. P is the probability that I get it correct. Probability of success, technically is what that is. So the probability of success, exactly 7 correct on a 10-question multiple choice test with 4 choices. There's my key. So if I have 4 choices, we're assuming only one of them is the correct answer. What is the probability that I get it correct if I'm just guessing? 1/4, right? Or 0.25. Right, 4 choices. I can get one of those is correct, 3 of them are wrong, 0.25. And I'm wanting 7. So n is 10, p is 0.25, and x is 7. So let's scroll over here. Let's pull it in live, although I don't think you need to see this one live. Let me go back. Distribution, binomial, and again 10, comma, 0.25, comma, 7. Let me get 0.003. So the probability of exactly 7 is 0.003. We can run 0.0031 if we want. What if we had 5 choices? How would this change it? What would change up here? 5 choices changes the, not the number, I still have 10. I'm still wanting to get 7 correct. It's going to change my probability. So if I have 5 choices, what's my probability going to be? I can press second enter and go back up there. It's going to be 20%, right? Again, 5 choices is 1/5. So again, if I have 5 choices, 1 choice, 2, 3, 4, 5, only one of them's correct. So 1/5, which is 0.2. Press enter, and we get, if I would write that out, it'd be 0.0007, we'll say 79. So maybe you can interpret scientific notation. That's times 10 to the -4. So if you put the probability as 7.86, I know you've kind of missed it all, right? I mean, probabilities are always between 0 and 1. So always look for that scientific notation if you see something like that. Okay. I gave you a screenshot of that. I forgot I did that. So 0.0079. Same thing I had here. Sorry, that's covered up. Example 3. Find the probability of getting at least 7 questions correct on a 10-question multiple choice test that has 4 possible choices. So at least 7. So think about, what does that mean, at least 7? At least 7 means 7, 8, 9, or 10, right? So I think you could probably see one way to do this. You could just find each separate problem, right? Find 7, find 8, find 9, find 10, and then add them up. Let me show you a couple of different ways to do that. Okay, so we go to Binomial PDF, and we put all that in. Now let me show you. Let me actually do this one live for you. So clear that out. So again, second distribution, it's 0 for Binomial PDF, and then it's 10, comma. We're back to 4 choices, 0.25, comma. And this time, if I want a list of them, I could just put 7, get the answer, write it down, and keep going. But we can be more efficient than that. So I can use these little squirrely braces here. Let me blow this up a little bit so you can see what I'm talking about. Right here. So if you press second parentheses, you'll get this little open brace here. So I've already put my comma, and then put second brace, and then actually put in, and here's the syntax here, you just put in all your x's. 7, 8, 9, 10. And then make sure you end the brace, and then end the paren. Okay, then I could just press enter, and then I can use my right arrow and scroll over. So there's the first one, we should recognize that number. There's my next one, there's my next one, and my last one. Notice they're on scientific notation. Now you may want to change your rounding. We've looked at this before. I can press mode, maybe round those out to 4. I mean, the problem is they get really small fast. So I don't know how well this is going to work. Let me repeat this. So 0.0031, at least it rounds the scientific notation for me a little bit. So I don't have to look at all those numbers. And then I write those down and add them up. So that's sort of the longer way to do it. We could store these in to L1 and have the calculator do this for us. So what I mean by that is I can go to, let me pull that back up again. So we put in, let me clear this out. Okay, so there it is. And rather than me have to write those down, I can store those values. So I press the store button, STO, down here right below the LN, beside the number 1. Gives me a little arrow. And I'm going to store these in a list. So I can store these, I can pop them into L1. And then press enter. So it gives me the same thing I got before, except now, watch what happens when I press stat and enter. There are these numbers right here in L1. So again, there's 7, 8, 9, and 10. Now how do I get those to be added up? You've done this before. We just have never looked at that piece before. Stat, calc, one variable statistic. So press 1. We'll do L1. Press enter. See this sigma right here? That means sum. So we're summing up the x's. The x's are what's in L1. So we get 0.0035. So that's kind of cool, right? I mean, we don't have to worry about, and it's particularly nice if you had like 15 numbers to write. That'd be a pain. So make sure you sort of learn how to do it both ways, and then hopefully you can pick the easier of the two. And I give you some screenshots here so you can have some nice notes. Okay. So again, the probability of at least 7 correct answers is about 0.0035. About 35 out of 10,000 times would someone get at least 7 by just randomly guessing. So there's another way. So maybe there are 3 ways to do this. I hesitate to give you all these ways, but this way is really a slick way to do it, sort of all in one, where we don't have to use so many functions. Is we can use a binomial CDF as opposed to the binomial PDF. That C stands for cumulative. So the C stands for cumulative. We're going to go ahead and add all these up, and it'll do that for you. So what the CDF syntax will sum up all the probabilities. So we put in 10, 0.25, 6. It'll sum up all the 1s through 6. So it's going to give us 0, 1, 2, 3, 4, 5, and 6. We actually want the exact opposite of that, right? We don't want 0 through 6. We want 7, 8, 9, and 10. So what we do is we subtract from 1. So we just do 1 minus the CDF 10.25, 6. I know that's confusing. So if you're thinking, boy, I don't get that at all, nobody gets it. So don't get frustrated when you don't get something right off the bat. Nobody gets it right off the bat. It takes patience, time. We'll do 20 of these, and then it'll begin to sink in. But I've got to start somewhere, so I started here. A lot of times we think we're unique when we're doing some problems. Some people say, I can't do word problems. No, I'm not good at word problems. Nobody's good at word problems. Nobody. So you are in the majority. I'm not good at doing binomial CDFs. Nobody is in the beginning. So you're in the majority. Don't think that somehow you're special in that regard, that you're not good enough to be able to get this. It takes a lot of practice to go through and think about these. And we'll do several of these in class, and you'll begin to pick it up. Make sure you're bringing your calculator to class, things like that. So again, we get the same thing on the 0.0035. Example 4. According to the Information Please Almanac, 80% of adult smokers started smoking before turning 18 years old. Suppose 10 smokers, 18 years and older, are randomly selected, and the number of smokers who started smoking before 18 is recorded. So explain why this is a binomial. So again, we go back to that original definition there of binomial. Fixed number of trials. I've got 10. I select 10. Right? I'm not selecting people until I find a certain number of smokers. I go ahead and select 10. Fixed number of trials. Only 2 outcomes. You smoked or didn't smoke. I'm not asking them how many did you smoke or something like that. Trials are independent. We're assuming these are independent. We're assuming we're not going into a household and asking all 4 people, because more than likely, if one person smokes, there's a greater likelihood of somebody else smoking. So we're assuming these are independent, and the probability of success is the same for each one. We're told 80% of smokers started smoking, so 0.8 is our probability. Okay, so for part B, find the probability exactly 8. So if I do that, let's start labeling. And I need to find my N, a P, and an X. Some books use K there, so hopefully I won't slip up, but I think our book uses an X. Okay, so find the probability of exactly 8. So what is N? N is the total number of trials. I've got 10. P is the probability. It says 80%, so write that as a probability. I get 0.8. X, I want how many? Exactly 8. So can you figure that out? I think I've actually worked this on the next slide. Let's see what we got here. Y binomial. I sure did. Fixed number of trials. Independent trials. Only 2 possible outcomes. Started before 18. Did not start before 18. And the probability of success is the same for each trial. I already kind of went through that. Exactly 8. Again, the syntax N, P, X. We've already labeled our N and X. And there we go. So it's a probability of about 0.302 that a random sample of adults, exactly 8, started smoking before they were 18. So about 30% chance. How about at least 8? What does at least 8 mean? So you can think about this one. What does at least 8 mean? At least 8 means 8, 9, or 10, right? Right? At least 8 means 8, 9, or 10. So let's use that binomial CDF, and again we'll subtract it from 1. So whenever we're doing at least, we can use binomial CDF, subtract it from 1. If you're doing at most, you can just use binomial CDF. Maybe I'll tag on a question here at the end. So we're going to find the sum of the first 7, which is the binomial CDF, 10, 0.8, 7. And we can go at the same step, I can do 1 minus that. There's a probability. So a random sample of 10 adult smokers, there's about a 67.678 probability that at least 8 started smoking before they were 18. You could have alternatively done 8, 9, 10, added up. You get exactly the same number. How about fewer than 8? So again, we can use binomial CDF, but this time we don't need to subtract from 1, right? Because CDF actually adds up from 0 all the way to x, whatever that x value is. So just put it straight in. Again, fewer than 8 means 0, 1, 2, 3, 4, 5, 6, 7. So 7 is our x in this case. So in a random sample of 10 adult smokers, there's about a 0.322 probability that fewer than 8 started smoking before they were 18. Between 7 and 9, again, what does that mean? And this probably should have said, it may have said it in the problem, inclusive. Because if we said between 7 and 9, we didn't say inclusive, that just means 8, right? So between 7 and 9, inclusive. So we could use binomial PDF, just sum those 3 values, or you can use binomial CDF and subtract. The CDF and subtracting, it can get a little confusing. You got to really know what you're doing on these, right? So again, how can I do this? I'm just going to think through. If I wanted to subtract it out, I could find the sum between 0 and 6, and then do between 0 and 9, and then subtract out. And that's what I do. So I do 0 to 9 and subtract out 0 to 6. I know for many that that's sort of a lot of, that can get tricky to think about. Again, binomial CDF sums up from 0 all the way to whatever number we put here. In this case, we put a 9. And then CDF here, again, it puts a 6. So if I wanted this, I'm going to write this down. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We are wanting between 7 and 9 inclusive, so we're wanting these values right here, right? So what can we do? If I knew from 0 all the way to 9, that would be, between 0 and 9 inclusive. But I don't want between 0 and 9. I want between 7 and 9. So I just take this value right here and subtract out. I subtract this one right here, between 0 and 9, and subtract it from this one. That's what I've done down there. Or you can do this way. The PDF, put it in L1, and just sum it up with the 1 var stats. See, same number. Some will find the CDF easier, some will find the PDF easier. It's up to you. Example 5. I don't know how to pronounce this. Dipacote. So I don't know how to pronounce that. Dipacote, whatever. Dipacote is a medication whose purpose is to reduce the pain associated with migraine headaches. In clinical trials of this drug, 2% of the patients in the study experienced weight gain as a side effect. A random sample of 30 users of this drug is obtained, and the number of patients who experience weight gain is recorded. Maybe some of you nursing majors can help me pronounce that sometime. Okay, I think it's also a drug used with epilepsy. I've heard of it, so find the probability that exactly 3 experience weight gain as a side effect. So let's go and begin labeling some of these things here. This is very similar to the last problem. It'd be a good idea if you pause the video, see if you can do these few problems here. Welcome back. How we do? Hopefully use the calculator. So we've got 30. So again, my n is going to be 30. What's the probability that I actually select one of these patients? Exactly 3. We got 2%, so p is going to be 0.02. Don't put 0.2. And then what is x going to be? In this problem, it's going to be 3. So in this case, x is 3. Okay, so exactly 3. So again, n was 30. P was 0.02. And in this case, x is 3. So let me just do these live. I don't think I have screenshots for you on this one. The screenshots take a long time for me to do, so it's a little quicker for me to do it live. I like to have at least one of those in your notes for you, though. Okay, so hopefully you're getting better at knowing what this is. Second distribution. Binomial, we're just doing 1, so we do the PDF. And then 30, comma, 0.02, comma 3. If you put it in any other order, it's going to give you the wrong answer, so it's hard to mess that one up. But just remember alphabetical order. 0.0188. So the probability that exactly 3 out of a sample of 30 experience a weight gain is 0.0188. So about 2%. Find the probability that 3 or fewer experience weight gain as a side effect. So what does that mean, 3 or fewer? So 3 or fewer means at most 3, or 0, 1, 2, or 3, right? So that's what x is going to be. N and p are the same. So here's where I have my choices. I can either use PDF or the CDF. Let me show you the PDF one. So again, go to binomial, or sorry, distribution. PDF is 0, and then put it in. We had 30, comma, 0.02, comma. If I want to do all 4 of these numbers at the same time, I can use little braces. If you're going to do the PDF version, I definitely recommend you at least do it this way. We'll close those braces, close the paren. Let me go and store it. No need for me to have to add those numbers up by hand. We'll pop this into L1. Press enter. So it'll give those values down there, and again I've rounded to 4 decimal points just so I don't have to look at so much. So that's not too bad to add up, but I've already got it. If I look here in the stat edit menu, right here in L1, there are my numbers. So if I go to stat calc 1 variable statistic, I'll put L1 just for insurance. There's my sum, 0.9971. So a 99.7% chance that 3 or fewer experience side effects. So pretty likely. Let's do it the CDF way. So again, the CDF, second distribution. It's binomial CDF, which I think it's that A. Yes. Binomial CDF, the same thing, 30, comma, 0.02, comma. Remember, CDF gives me the cumulative from the 0 all the way up to some number. That's what I want, 0 up to 3, and including 3. So if there's any justice in this world, this number, when I press enter, will be the same one as this one. 0.9971, look at that. So I leave it up to you which way you do it. The CDF one can get a little confusing if we're doing more or if we're doing in between numbers. Okay, so find the probability that 4 or more experienced weight gain as a side effect. So what's 4 or more mean? So 4 or more means 4, 5, 6, 7, all the way up to 30. Right? So that's what x is equal to. So how am I going to handle this one? I'm going to do this one a CDF way. Because even with the binomial PDF, I'm going to have to put in binomial PDF 30, comma 0.02, comma 4, comma 5, comma 6, comma 7, all the way to 30. Store that in L1. I don't want to do that. But if I do CDF, what am I going to find? I want to find all the way up to the number right before this one, right? So I'm going to find the CDF, binomial CDF. I'm going to do 30, comma 0.02, comma 3. Then I'm going to do 1 minus that. So I'm going to go and put 1 minus, and then binomial CDF 30, comma 0.02, comma 3. So why don't I go to 4? Because I want 4 to be included in what I find. 0.0029. Now sometimes you'll get lucky and get the right answer if you put a 4, because those probabilities become very small very quickly. So you sometimes may get the right answer there, but really be careful in these. I'm going to want you on the homework, test, and things like that to write this out so I can know what you're putting in. That way, if you have this in and for some reason you write down the wrong answer, I can do some partial credit, because I'm not making you use that formula, right? The formula involving the combination. We use the x there. In combination x, p to the x, q to the x minus 1, x minus n minus x. Yeah. So we're eschewing the formula in lieu of the calculator. Okay, find the probability between 1 and 4 patients inclusive experience weight gain as a side effect. So again, between 1 and 4 means what? Means 1, x is going to be 1, comma 2, comma 3, comma 4. So I could do CDF, I could do PDF, either one. I'll show them both to you. So let's start with the PDF way. So PDF, again, since I only have 4 numbers, PDF's not that, it's not that hard to put those in. If I had 40 numbers, I don't want to put 40 numbers in if I can avoid it. With 4, it's not that big a deal. Second vars. We'll do PDF, and again, PDF gets individual probabilities. So again, we have 30, comma 0.02, comma, little squirrely brace. I'm getting ready to put a bunch of numbers in here. 1, comma 2, comma 3, comma 4, then end. And then I want to store these. Don't forget to store it. So store into L1. I'm confident it's in there. Well, let's just be sure. Stat edit, and there they are right there. So stat calc 1var L1. Oh, not 1, L1. Again, I'm looking for that sum, 0.4542. Okay, now if I want to do the CDF, I'm going to do 0 and up to what? I'll let you pause it and see if you can figure out how you could do a CDF on this one. Okay, welcome back. Did you get it? So we're going to go from 4, because when I put the 4 in, what's that give me? That gives me 0, 1, 2, 3, 4. Then I subtract out the 0, and I get 0.4542. I could have done a PDF there since I'm just evaluating one value at 0. But just to sort of keep in with, keep it consistent, you're always going to be subtracting the CDFs. Once you see how this works, it's not that bad. We're just subtracting out. Okay, E. Find the probability that 20% of the sample experienced weight gain as a side effect. I should have had a period in that. Okay, so what does that mean? So now I've got another percentage in here. And just kind of go back to what we're trying to find. Again, we need to find the N, P, and X. So my N is still 30, P is still 0.02. That hasn't changed. Just to find the probability that 20% of the sample experienced weight gain. So what's 20% of my sample? My sample's 30, so 20% of 30 is what? 6. 10% is 3, so 20% would be 6. So sometimes it can be worded a little bit differently. They may not say find the probability that's 6. It may just give that in percent. So it says that exact. So we're looking for exactly. So if it's an exact, we go to PDF. So I'm going to go to second distribution, binomial PDF, and you will get good at these if you work maybe a dozen of them. 6. So we get a pretty small number here. 0.00023. So very unlikely. We would expect it not to be likely. Only 2% of the population is, so in a sample of 30, we expect about 2% of that population. So 20% is pretty high. Okay, example 6.